So the next topic we will be looking at is basically the internet protocol like IP. So the basic IP addressing we have seen IPv4 and IPv6. So we'll just see like what is the header used for like IPv4 and IPv6 types. Okay, so for internet protocols, it is basically used like IPv6 and IPv4. So for that, what is the basic format of their headers? Headers in the sense like once we are going to use the IP, they contain different informations. So how that informations are contained, that is with respect to a header of the IPv4 and IPv6. So we will be starting with the first one, IPv4, and then we will be looking at IPv6. What is its header format? We will explain each of the component of that header one by one, basically. So here in inter networking, like basically the internet. So in this section, what we will going to discuss is I will be discussing the internetworking, connecting networks together to make an internetwork or an internet. So how internetwork works. Here in internet model, the main network protocol is the IP, that is the internet protocol. So in network model or the network layer, basically the IP is one of the important uh, protocol that is basically used. So here it is showing you out like how we can consider connection between source and destination at the physical and the data link layer. So if we are having the physical and data link layers inside a network, then it will be, first of all, in that case, if we are using physical and data link layer, it will be basically used for uh, local operation basically, or it will be having an operation that will be basically taking place with hope to hope type of delivery. So if this is the complete structure looking like, so here A is there, that is source, and destination is D, the destination. So between source and destination, we are having the switches S1, S2, and S3 likewise. So if the data is being transmitted from source to destination, like from A to D, then it will be going to like hope to hope delivery. So we have already seen that. So that will be taking place. So these two layers are jointly responsible for data delivery on the network from one node to the next. That is the basic idea. Okay. But if we are having uh, a case where we want to deliver the data from source to destination, but through different network. This is for a single network, having the same network that is operating on a local network. Okay, so source and destination are available on the local network, but if the source and destinations are available at two different networks, so then there is a requirement of a network layer. So here, network layer that is behaving like an internetwork. Okay, so here a network layer is responsible for host to host delivery. So here the host to host delivery is performed in case of physical and data link layer. Here basically it is having hope to hope delivery, and in case of network layer it is having host to host or end to end delivery basically. And also this network layer is used for routing the packets to routers or switches. So here the data is starting from the source A from the network layer going, and it is not dropping at the switches. It is going through the network layer of the switches, but finally reaching to the destination. But in the previous case, it is going starting with here, and this is the destination for this communication. So starting with here, this is the source, and then this is the destination. But in network layer, the direct host to host delivery is done. So at network layer, it consists of basically a source, a destination, and a router. In between the data that is being transmitted from source to destination. So how it basically behaves, so how a network layer basically works at different locations, like at source and destination and the routers. So at network layer, so the network layer at the source is basically responsible for creating a packet from the data coming from another protocol. So any data coming from another protocol, some upper layer protocols, then it will be basically creating a packet out of it, okay, with the help of routing table. So with the help of routing table, it will be basically creating a packet. The network layer at the destination is responsible for address verification. So address verification in the sense, so at the destination side, this will be done like if it is coming from the lower layer, that is from the data link layer, the packet is coming, so it will be processing, and it will, after processing, it will be basically sending it to the upper layer. So address verification in the sense if it is the destination. So if destination is this one, it will be verifying the address of from the packet that is it is receiving. So from there, it will be matching the destination address. If it is matches, it will be processing it in and further forwarding to the higher layers basically. So in the network layer, at the switch or the router here is responsible for routing the packets. So the role of router is to uh, give a direction to the coming packets in the direction that is given into their routing table. So based on the routing table, the router will be basically directing the packet that is coming from a particular node port to some other ports to the destination side. So when a packet arrives, the router or the switch consults its routing table and finds the interface from which the packet must be sent. So that is governed by the routing table. So the packet, after some changes in the header with the routing information, is passed to the data link layer again. So it is like router is there. So one side it is like from the data link layer, it will be taking the packet. Okay. So it will be processing and then it will be sending again to the data link layer with some routing information that will be based on the routing table. So this was the basic working of network layer. So with the help of this into the mind, we will be basically going to see what is IPv4. So yeah, that's one note is there. So switching at the network layer in the internet uses the datagram approach to packet switching. So in the sense, once we are going to have a switching of the data that is in the form of packets, so at the network layer, so that switching is basically done with respect to the datagram approach. So we have already gone through, so datagram approach, virtual circuit switching. So switching techniques we have already seen. So here the networks basically will be using the datagram approach for switching the packets. And here the communication at the network layer is network in the internet is connectionless. So in the sense, because it is in the form of packets, so these packets are transferred in all directions. So if a router is there and different, it is connected with some different routers. And suppose here is the destination, we are having the destination, and here the source is there. So if a packet is sent, this is the packet. So this packet will not be like going through a set of path only. So it will be going in all directions. So it is like a connectionless. So it will be sending the packets in all directions without any specific connection. So that's why that we have already seen in like datagram. What is the datagram switching approach? So we have already seen that. So the similar approach is used into IPv4. So what is IPv4? Is like Internet Protocol version 4. So IPv4 addressing we have already seen, but we will be just seeing like what is its header, what is the structure of its header, and what different components are there, and how it basically responds for the working of this IP, this Internet Protocol. So IPv4 is basically used for the delivery mechanism. Delivery mechanism in the sense delivering the data. For delivering the data, we will be using this IPv4. So that is delivery mechanism that is basically used by the the TCP/IP protocol. So TCP/IP protocol is going to use the Internet protocol version 4 IPv4 as the delivery mechanism. Okay, so here IPv4 is an unreliable and connectionless datagram protocol. So connectionless datagram protocol, and it is unreliable. So why it is unreliable? Because it is having no error control or flow control mechanism. So there is no error control into here. So for error control is being done at the data link layer. At the network layer, there is no error control. So that's why it is considered to be like an unreliable one. But it works at a best effort delivery service. It's meaning like it basically have no error control or flow control, but uh, it has some error control only for the header portion. Okay, so best effort in the sense it will be trying its best to deliver the packets without any error. So here is the position of IPv4 inside network layer. So it is a part of network layer. So inside network layer, it is the IPv4 is available along with some other protocols. So yeah, so we will be starting like what is the basic datagram format or the header format in case of IPv4. So in IPv4, basically, so once we are having different layers, so we send the data. So we have a data. Along with that, some headers are added. So along with the data, a header is added. So what this header is there at the network layer if it is an IPv4. If it is using an IPv4 type of delivery mechanism, then what will be the header? So what is inside this header? So this header is generally considered to be having a size of 20 to 60 byte. So header is of size of 20 to 60 byte means this is the minimum size of the header and this is the maximum size. So header in case of IPv4 can be of either minimum size of 20 byte, maximum size of 60 byte. Along with that, so if header and data, that will be considered as a packet. This will be considered as a packet. So one packet can be having a size. So maximum size and minimum size of a packet can be like, so minimum size can be this one and maximum is this one. So this is 65536. So this is the maximum size and this is the minimum size of a packet into IPv4 delivery mechanism. Okay, so here if this is the maximum size and this is the minimum size, then the maximum size of data, so this is the size of the packet, but the maximum size of data is like we'll be subtracting 20 from here, so it will like 65516 byte. So this will be the data, the maximum size of data that can be available. So minimum size can be 0. So data can be 0. If the minimum size is 0, data is having minimum size 0, then the size of the packet will be 20 byte. That is the header. That is the minimum. So this is with respect to the size of header and data. Next, we will see like inside this header, what different components are available into this header. So this header is divided into this complete set of different components. So with respect to each component, there is a byte is given. So or the size of each component is available. So it is VER. This is basically the version. So version in the sense, so if it is this version will be represented by 4 bits. So one thing here, so it is minimum size of the header is 20. So how this 20 came? So 20 byte is it is basically. So 4 bit, that is 1 byte, 2 byte, 2 to 4 byte, 4 to 6 byte, and then 7 and 8 byte, 9, 10, 11, 12 byte, and IP addresses. So IPv addresses are basically 4 byte. So 12 plus 4, it is 16 plus 4, 16, 20. So total is 20 byte. So 20 byte is the minimum size and maximum is 60. So how this maximum 60 came? So in maximum 60, 20 will be the this one, this will be the 20 byte and this option. So option can be ranging between 0 byte to 40 byte. As its name is there, option, so it is an optional one. So if it is having the maximum 40 byte, then the maximum size of the header will be 60 byte. 20 plus 40, 60. If the option is not used, then it will be of 0 byte. Then the minimum size of the header will be the 20. So minimum size came once there is no bit for the options. So now we will see what are the different components and how they are going to play its role. So here version. So this version is basically going to indicate like what version of IP is being used. So if it is IPv4, that is IP version 4. So this 4 bit will be representing like 0, 1, 0, 0. So 0, 1, 0, 0 is equivalent to 4 into decimal. This is in binary and this 4 in decimal. So always if it is an IPv4, so this version 4 bits will be always 0, 1, 0, 0. This is fixed for IPv4. If it is IPv6, then this will be representing the 6. So 4 bits will be representing 6. So what is the role of this? So whenever the data needs to be sent, first of all, the version will be checked. So based on the version, so once the destination device is going to identify its version, with respect to that, it will be understanding like next 4 bit will be coming out to be this header length. Then next 8 bit will be the services. So with respect to version, all the bits will be having its specific meaning. If the version is different, it will not be interpreting it with respect to whatever the information, whatever the software or the hardware components the particular destination is having. It will not be interpreting it. It will be just discarding the data, or it will be dropping the data if the version is not matched. So this is the basic idea of using the version. Next is header length. H length, it is basically header length. So header length is of 4 bit. So here the header length is 4 bit in the sense. So what is the meaning of this header length? So header length is like it is going to tell like what will be the length of the header basically. So header length is basically identified by like here we have already seen like the minimum length should be 20 for the header and the maximum is 60. So how this 4 bit is going to indicate what is the length of the header? So 4 bit h length is basically this is header length. It is represented by 4 bit. So 4 bit can be 0, 0, 0, 0. Then maximum it can be 1, 1, 1, 1. So minimum it can be 0, maximum it can be 15. So if it is 15, how it will be representing 20 byte. So how it is basically is, it basically whatever is the information represented by this 4 bit, suppose the 4 bit is 0, 0, 0, 0, or suppose the 4 bit is 0, 0, 1, 0. So 0, 0, 1, 0 means it is 2. So whatever is the value, it is 2. So 2 will be multiplied by 4. So 2 is multiplied by 4, that is 8. So this 8 is going to be the byte of minimum byte or length of the header. But here the length of the header is defined as minimum is 20. That means if the 20 is the minimum length, at that time what will be the value of 4 bit? So that will be given by like 20 divided by 4, that means 5. So minimum value of this header length will be like 5. So 5 in the sense 0, 1, 0, 1. So minimum value of this h length will be 0, 1, 0, 1. So whatever is the 4 bit value, its decimal equivalent will be representing After multiplying by 4, that will be the total number of bytes available into the header. So h length indicates the length of the header. Next is the service. Service is basically represented by 8 bits. So this service is basically how this basically the service is represented. So for representing the services, there are two different identifications. So one can be like, this is the older format. So first of all, this service is represented by 8 bit. So in one of the format, there are two ways this 8-bit services can be represented. The first one is called like service type, and the second one is called like differentiated services. So in the first case, this is the first one, the structure of the first category. It's basically like this 8 bits can be represented by two methods. Either we can use service type or we can use differentiated services. The differentiated services having the format like this. This is the format, and service type is having this as the format. So in that case, if suppose we are having the service, we are representing the services bits as service type. In that case, starting are the most significant 3 bits, or the last 3 bits will be representing the precedence. So what is the meaning of precedence? So precedence here is the datagrams with the lowest precedence are discarded first. So in the sense, so precedence in the sense it will be giving a preference to different data. So suppose there is a congestion into the channel. So if there is a congestion into the channel, so which packet should be dropped, that is decided by this most significant 3 bits. So each packet will be given a preference or precedence. So based on like 3 bits are there. So maximum is starting with 000, maximum 111. So if suppose this packet is having a preference like 7, and this one is having first, then if there is a congestion, the first one will be retained into the communication, and seventh one will be dropped. It will be dropped. This is the basic idea of the precedence. Next is called TOS bits. So this TOS bits, so TOS basically stands for like types of services. TOS bits. So types of services means what type of services the particular packet is going to be serving, okay, or the packet is going to be serving. So that will be given by the header. So header, this portion of the header will be indicating what type of services this packet is going to be performing. So here D stands for minimum delay, and T stands for maximum throughput. R stands for maximize reliability. C stands for minimize cost. So what is this meaning? So if these bits can be either 0 or 1. So these bits can be 0 or 1. Similarly, this can be 0 or 1. Similarly, this can be 0 or 1. And this one is basically reserved one. So if delay, so this is minimized delay. So if any header is there that is having minimized delay as 0, that means it will not be minimizing the delay. If it is 1, that means this packet is going to have the minimum delay. Minimum delay means it should be given a preference. So what is the meaning is like D is like the delay. So activities requiring immediate response. So if any activity is there that is requiring immediate response, we should be making D as 1. So similarly, T is for throughput. So if any services or activities are there that send bulk data. So if someone is sending bulk data, that means it requires high speed. So if it requires high speed, then this T bit should be 1. That will be indicating like maximized throughput is required for this packet. Next one is maximize reliability. R stands for reliability. So if some R is like reliability, so some management related activities are being performed, means some control related activities are being performed. In that case, reliability is must. Reliability in the sense, suppose whatever data is being sent, it should be having a reliable data at the destination also. There should not be any data loss. So if some control related data or management related activities are being performed, at that time the R will be, or R should be 1. Similarly, minimize cost. C stands for cost. So if any uh, activities are there, that is called like a background activity. So some background activities are there, so that is not that important. So in that case, the we can have like minimize, we can implement to have a minimum cost. So in that case, C bid will be 1. So but yeah, so in any like service type, this D, T, R, C cannot be 1, or like more than 1 bit cannot be 1 here. So either D will be 1, or T will be 1, or R will be 1, or C will be 1. No two of the bits can be 1 at one time. So this is the basic idea for representing the services type of 8 bits. Likewise, this is called like service type. Next one is differentiated service. So the same 8-bit can be represented in terms of differentiated services. So this differentiated services, how it basically works. So these two are basically like reserved one, or basically we can call it reserved one, or we can call it like unused. It is basically unused here. Unused means it is not basically used. The remaining are being used. So these 6 most significant bits will be used. That is called the code point. Okay. So here, when the 3 rightmost bits are zeros, so 3 rightmost bits are zeros. Okay. The 3 leftmost bits are interpreted the same as the precedence bits in the service type interpretation. So this, now this will be indicating the precedence, similar to the precedence. The next case is like when the 3 rightmost bits are not all zeros. So if these 3 bits are not all zeros, in the sense, so any one is non-zero, then in that case, the 6th bit defines 64 services. So this 6 bits can have total like 6-bit variations are there. So total 64 combinations it will be indicating. So these 64 combinations will be indicating 64 services. So what these services are there? They are given in table 20.3. So these services are given like 20 point, yeah, these are also the services TOS bits. So that is for this one. So 4 bits are there. So if the 4 bits are there, 000, it is basically ICMP protocol. It is going to explain the ICMP protocol in normal mode, then boot P, then NNTP. So for different protocols, these TOS bits are defined likewise. Okay, so always only 1 bit will be 1. No two bits can have the 1 into the same combinations. Okay, TOS bits, only 1 bit will be 1 at a time. So values for code points. So code points, it is going to say like if there is first out of the 6 bits, the first bit is 0, and remaining bits are anything. It will be behaving like an internet. So it will be going to assign the services related to internet. So if it is 1 1 and the remaining 4 bits are anything, this is 1 1, it is going to have local services. So like if it is 0 and 1 it is there, so it is temporary or experimental services are there. So this is how the code points will be going to give the services related informations. Okay, so this was the services. Yeah, next one is total length. So total length is of 16 bit. So 16-bit total length. So this total length will be explaining the total length of this header as well as the data. So you can consider here. So the maximum value of the header and the data is 65536 basically, or it is like in that case it is basically ranging between 0 to 65535. So total will be 65536. So its meaning is like that is equivalent to 2 to the power 16. So 2 to the power 16 is going to be value 65535. Okay, so starting with 0 to this one. So 2 to the power 16 will be 65,536. Okay, so this much of the size can be there. So total length of the header as well as the data is going to be indicated by 2 to the power 16. Okay, so these points will be helpful once we will be understanding some of the numerical questions. So these points will be helpful to identify like how many or what is the size of the header, what is the size of the data. Okay, so total length will be indicating the total length of header as well as the data. Next is this identification, flags, and fragmentation. So these three components are considered as the part of fragmentation. So what is fragmentation? So basically, we know like once data, if suppose there is a network layer, then data link layer, then physical layer. So if any data is there, so along with the data, we are having header. Okay, into the network layer. But once it is coming to the data link layer, so this portion will be equivalent to a data here, and then some trailer bit and header bits are added. So there is a fixed size of this data into data link layer or a particular layer. There is a fixed size for this data. So if suppose the data portion is very having higher length, then what we need to do is we need to break this complete data so that it should be suitable to be accommodated by this particular data portion of a particular layer. So in that case, there is a requirement of fragmentation. We will see that part into later on. Okay. So one by one, we will be looking at different components of this fragmentation part. Next is time to live. So time to live is another point that is basically it is a value. It is a value that is basically considered as 2 times the maximum number of routes between any two hosts or one for local network. So in the sense like suppose time to live is going to say like suppose this is the source and this is the destination. In between there are different routers. Okay, so whatever is the number of routers is there, then multiplied by 2. So 2 routers are there multiplied by 2, so 4. 4 will be the value that will be put into this 8-bit format. So this 8-bit can be ranging. So this 8-bit can be ranging between 0 to 255. That means total 256 values will be there. Okay, so ranging between 0 to 255. So this indicate like so from source. Suppose a packet is sent. So it will be coming to so once it is sent, it will be given a value. So it will be given a value. Suppose it is given a value 10. So in this time to live column, it is going to give the value 10. Suppose that means it can once it is passing by one router or switch, its value now will be dropped to 9. Next, it is going to here. Okay, so once after it here, its value will become 8. So this time to live is a 8-bit value, or in decimal we can consider it is a decimal value or 8-bit value that will be basically going to indicate the total lifetime of the packet. So or the how many switches or the routers it can pass through, a packet can pass through, that will be the time to live. Suppose this time to live value becomes 0. So if the time to live value becomes 0, then that packet will be dropped. This is the basic idea. So it is like if suppose a packet is there, it is traveling through all the different routers, but it is not reaching to the destination. So there is a limit, because if it keep on rotating through the router and router through the path, it can create a congestion. So to avoid this congestion, the time to live value is set to each packet, so that after certain hopping between different routers, it has to be dropped if it is not reaching to the destination. So this is the basic idea of time to live. So it is in 8-bit format. So maximum value it can be having like 255. Okay. So that means it can pass the data, the packet can pass through 255 routers, and then before that it should be reaching to the destination. Otherwise it will be dropped. So this is the basic idea. Okay. One more thing, like here, one for the local network. So if suppose you want to send, if the data needs to be sent, suppose the local network in the sense, so this is the source and this is the destination. So from source to destination it is going to be there. Okay, so this is, if it is connected to local network, so its value should be put as 1. So 1 in the sense, so if it is value is 1, once it is reached to one of the uh, device, its value will be reduced to 0. Okay, so now once it is 0, otherwise it should be reaching at the destination or it should be dropped. So for local networks, the value of time to live is put as 1. Next one is protocol, that is also going to be explained for 8 bits. So this basically defines the higher level protocols that uses the services of the IPv4 layer. So what are the different protocols that are going to use the services of IPv4 is governed by this 8 bits. So what these 8 bits are there, its value are given here. Yeah. Yeah. So these are the protocol field. So different services are going to be like ICMP, IGMP, SCTP. So it is of 8-bit value. So 8-bit value is basically having the range between like 0 to, it's 8-bit value 0 to 255. So in between 0 to 255, if the value is 1, it indicates ICMP. Its value is 2, it is going to indicate IGMP. So likewise, some random protocol values are given. So what protocol it is going to be there, that is given by the values ranging between 0 to 255 for 8 bits. Okay. So total length field defines the total length of the datagram, including the header and data. That is there. Yeah. And then header checksum we will be looking at later on. So yeah. So type of services, default services that are there, and value code points, total length, like data, total size of the datagram, basically total length of the datagram, including header as well as the data. Okay. So encapsulation. So we have already seen like what is encapsulation, what is decapsulation. So encapsulation, for performing the encapsulation, there is a minimum size of the byte that should be there. So for minimum size of byte, suppose the data is less, then suppose minimum size required is 46 and the data is less than 46, then there is a requirement of padding some extra bits. So that is the padding. So similar padding is also used here also. Yeah. So in this option and padding are there. So that comes like whenever there is a requirement of bits to satisfy the minimum criteria, we should be adding extra zeros. That is called the padding. That comes under the options and padding. Okay. So protocol field and encapsulate data. So here the same protocol field we have seen. So an IPv4 datagram can encapsulate data from several higher level protocols such as TCP, UDP, ICMP, and IGMP. So different uh, protocols it can incorporate. The IPv4 protocol carries data from different other protocols. The value of this field, helps the receiving network layer knows to which protocol the data belongs. So in the sense, if we have put the value of protocol field value, so if that is of 8-bit, so out of 8-bit, it basically indicates like if a particular packet is there, so that packet belongs to which type of protocol, that is given by this protocol 8-bit field. Okay, so for different protocols, the values are given here. Okay, so some questions are there along. After this question, we will be looking at like what is fragmentation. So here the question is an IPv4 packet has arrived with the first 8 bits as shown here. So the receiver discards this packet. Why? So why the receiver is going to discard? So it's just saying like first 8 bit. So it is first 8 bit. So first 8 bit, out of the first 8 bit, this will be the 4 bit and this is the 4 bit. So this 4 bit will be indicating the version. So it's binary equivalent. So it is 0100. So 0100, 0100 is equivalent to 4. So that means it is going to say like it is IPv4. Version 4 is there. So if it is version 4, then next 4 bits, that is 0010, is going to indicate the H length, like header length. So its equivalent is 2 in decimal. So 2 in decimal. So it is header length. So 2 should be multiplied by 4 to get actual header length. So actual header length is 2 into 4, that is 8 byte. But it is already we have seen like the minimum length of the header is 20 byte. Okay, so but here it is saying 8 byte, so it is not true. So if it is not true, that's why the receiver will discard this packet, because it will be understanding like there is some error into this packet. So the minimum number of bytes in the header must be 20. So the packet has been corrupted in the transmission. The receiver will be understanding like the packet has been corrupted, so it will be discarding it. The next question is, in an IPv4 packet, the value of H length is 1000 in binary. So 1000 in the sense it is 100. It is not 1000, it is 1000 in binary. So how many bytes of options are being carried by this packet? So this is the H length. So we need to find out what is its this is binary. Its decimal equivalent will be like 8. So 8 multiplied by 4, that is 32 byte. So this is the 32 byte is the length, H length, that is header length. So out of the 32 byte, that is the header length, the here is saying like how many bytes of options are being carried out. So we already know like minimum header length is 20 byte. So but it is 32 byte means there are some headers are there. So if there is no header, the minimum size of the header will be 20. So if there is options, then the size of the header will increase from 20 to some value that will be added, the value of the options. So whatever is the option value, so we have already seen here. So if option is there, option is ranging between 0 to 40. So 0, so this one is 20. So 20 plus 0 will be the minimum 20 byte. So but if it is its total length is more than 20 means there are some options are there. So in this example, so it is like 20 is the minimum for the header. So extra 12 bytes are there. So this extra 12 bytes will be for the options. So that was basically asked into the question. The next question, in an IPv4 packet, the value of H length is 5. So H length is 5 in the sense, so 5 multiplied by 4, that means 20 byte. So 20 byte is the H length. The value of the total length of the field is 0 cross 0028. So this representation is basically used for hexadecimal. This is hexadecimal representation. So this 28 is in hexadecimal. Then we need to convert it into decimal basically. So if we are going to convert it into decimal, so it will be how it will be converted. So it will be 2 multiplied by 16 to the power 1 plus 8 multiplied by 16 to the power 0. So it is 32 plus 8 means 40 will be in decimal equivalent. So that is saying like 20 byte is the header, and it is saying like total value, total length of the field along with header and data. So header and data is 40. So it is asking for like how many bytes of data are being carried out in this packet. So 20 is header, total is 40. So 20 will be the data. 40 minus 20 will be the data. So these are the basic questions. So one more we will be looking at. So here IPv4 packet has arrived with first few hexadecimal digits as shown. So these are the first few hexadecimal digits coming from the header of the IPv4 packet. So it is asking like how many hops can this packet travel before being dropped? How many hops in the sense? So we have seen it is asking for like how many, what is the value of time to live? So time to live means how many routers it has traveled. So that will be like how many hops it is going to perform. So from the source, this is like first hop, then second hop, like third hop, it will be coming here. So this will be like third hop. So that hopes we need to find out how many hopes it is going to travel. So we need to find out like what is the time to live. So we need to find out like what is the byte number. So this is 4 means this is 1 byte, second byte, 3 4 byte, 5 6, this 7 8. So after 8 byte, this is the ninth byte. Time to live is the ninth byte, and protocol is the 10th byte. Okay. So in the question we need to see. So this is the first byte, second byte, third byte, fourth, fifth, sixth, 7, and 8. Because this is hexadecimal number, 4 and 5 is hexadecimal number. So each hexadecimal is having the 4-bit representation binary. So 4 and 5 total will be 8 byte. Sorry, 8 bit. So if it is 8 bit means 1 byte. So up to here 8 byte we have seen. So ninth byte is this one. Then 10th byte is this one. So ninth byte is going to indicate the time to live. So time to live is 0 1. Its meaning is here. So if it is 0 1, this means the packet can travel only one hop. Its meaning is it can travel only one hop. It is basically indicating the one hop, or it is basically indicating the local network. It is indicating the local network. Next is the protocol field that is having 02. So the protocol field is next byte, that is 02, which means the upper layer protocol is IGMP. So in the protocol list, 2 indicates for IGMP. So it is indicating like IGMP is the protocol. Okay, so next point we will be looking at is fragmentation. So what is fragmentation? So in this case, so fragmentation is going to indicate identification, that is 16-bit, flags, that is 3-bit, and fragmentation offset, that is 13-bit. Okay, and header is also remaining. So we will be looking at after fragmentation, we will be looking at the header checksum. Okay, so a datagram can travel through different networks. So whatever the datagram in the sense a packet can travel through different networks. So each router decapsulates the IPv4 datagram from the frame it receives. So it will be decapsulating it once it is receiving. At the receiver side, it's talking about. So whatever the frame coming from the data link layer. So at the receiver in the network, the data will be coming from the data link layer. This is the network layer. Then it will be the higher layer. So whatever the higher layer, it will be going here. So here the decapsulation will be there. Decapsulation will be taking place. So decapsulates from the frame it receives, then it processes it, and then encapsulates it into another frame to send it further. So yeah, but this is like a router it is talking about. So at a router, it basically takes the data from one of the data link layer. Then after processing, it will be sending it to another it will be sending it to another data link layer. So this is basically the router. It basically does. The format and size of the received frame depends on the protocol used by the physical network through which the frame just arrived or just traveled. Okay, so whatever the frame size, format and frame size will be there, that will be depending on from which network it is coming. So it can be having some different network, and it should be going to some different network. So these can be having some different uh, formats and size. Okay, so an example is here, like if the router connects LAN to WAN, it receives a frame in the LAN format and sends the frame into the WAN format. So the formatting is being done basically. So in the formatting is like if a LAN is the format, it can have a data in of having some different size, and here in WAN format the data can be of different size. So how this sizing is basically done at the router side, that is done with respect to the fragmentation. So fragmentation will be done at the router side. Okay, so it will be, if suppose this is having higher size, okay, so higher size is there, and here the smaller size is required. So it will be doing the fragmentation of this to make it the smaller size. Okay, so this is the basic idea. Yeah, maximum transfer unit. So what is the maximum transfer unit that we have already seen? Like an IP address, sorry, the IP datagram is there, or it is like a packet is there at the network layer. Network layer, there is a packet. So this packet will be going to the data link layer. So at the data link layer, this packet will be having like a data, and some header and some trailer bits will be added. Okay. So here this is like maximum transfer unit. So it is saying like the maximum length of data to be encapsulated in a frame. So because the size of the frame is fixed, okay, in that case, so what is the maximum length of the data that can be encapsulated? That will be called like MTU, that is maximum transfer unit. Okay? So whatever the data packet coming out to be there at the data link layer, the whatever is the packet size, suppose its size is suppose 100 byte, but the MTU here is only 10 byte. Means at the frame size it can only accommodate 10 bytes, so it will be breaking it into different frames, okay, or different fragments. So the individual fragments will be coming out to be here, and then that will be processed at the data link layer. So here when a datagram is encapsulated in a frame, the total size of the datagram must be less than this maximum size, means MTU. So whenever the encapsulation is being performed, the total size of the datagram, IP datagram, must be less than the maximum size of this MTU, maximum size of the encapsulated data that is into the frames, which is defined by the restrictions imposed by the hardware and software used in the network. So based on the different hardware and software, this restriction is defined. Means for different softwares and hardwares, there are different set of values of MTU, that is maximum transfer unit. So the value of the MTU depends on the physical network protocol. So whatever the different physical network protocols are there, based on that, the MTU will be depending on. So for other physical networks, we must divide datagram to make it possible to pass through these networks. This is called fragmentation. So same thing, once we want to pass this 100 byte data, but it can accommodate only 10 byte. So we need to do the fragmentation, or we need to divide this 100 byte into some smaller uh, size of data that should be accommodated by this MTU value of a particular physical network. Okay, that is there. So this is the role of fragmentation. So how this fragmentation will be done? Okay, so here some MTU values for different networks are given, like hyper channel type of protocols are there. So the MTU value is 65535. So token ring type of protocols are there. In that the MTU value is different. Okay, so for different protocols, the MTU, that is maximum trans transfer unit, that can be having is different. Okay, so if there is different protocols and the IPv4 is going to use different protocols that is having different size of MTU, then there is a requirement of MTU. There is a requirement of fragmentation to accommodate here. So suppose token ring is there, it wants to communicate with the PPP. In that case, this is the MTU value. That means along with the 4464 is the data, there will be a header, or along with this header, we can call it like along with like header and data in token ring 4 Mbps. Here the total size will be 4464, but we want to communicate with PPP protocol. So here the header plus data will be having a size of 296. So this, if you want to encapsulate to this PPP protocol, we can't do this because it is having higher size. So we need to break this into some smaller fragments so that it can be accommodated into this protocol. So this is the basic understanding. Yeah. So next, in fragmentation, there are different fields. So we will be looking at one by one. So first one was identification. So what is the basic meaning of identification is like the same. So if a particular, like here we have seen, if a particular size of the data is there, so if we are going to fragment it, so once we are going to fragment it, means suppose this is the largest size. If we are going to fragment it, so it is suppose going to divide into 4 different fragments. So fragment 1, fragment 2, fragment 3, fragment 4. So all the fragment will be having different headers. Okay, so in each of the fragments, fragment 1, fragment 2, fragment 3, fragment 4, it will be having header and data. So each header of this larger datagram or the larger packet, it is divided into different fragments. That is another packet itself. But here there is an identification bit. So identification is a 16-bit value. So this identification bit, that is 16-bit, whatever is the identification value is there here. Suppose it is 240400 is the identification value, 16-bit field. The same 2400 will be identification value for all the fragmented part. This is the basic idea of identification. So it will be able to identify like if any frame is there or any packet is there that is having the same identification value, then its meaning is all these fragments are part of the same packet. This is the basic idea of identification. The same is given here. So here, when IP4 protocol sends the datagram, it copies the current value of the counter to the identification field and increments the counter by 1. That means it is this 16-bit field is a unique value. Okay, that is basically remains same for one particular packet, and if it is fragmented, all the fragmented parts will be having the same identification value. So for say some other packet, so next packet is there, so this value will be incremented by 1. So that will be the identification value for some other packet. So that is coming out to be like 16-bit. So total possible data grams or the packets it can have is 2 to the power 16 packets it can name uniquely. Okay. Next is the flag. So flag is the second part in case of the fragmentation. So this flag is of 3-bit basically. So it is of 3-bit. So out of the 3-bit, most significant bit is basically the reserved one. Reserved for some other application or some other values. Okay. So it is not used nowadays, but it is basically reserved. But here the remaining 2 bits, so one is D and one other one is M. So what D indicates? So D indicates like do not fragment. So do not fragment. What is this meaning? So if D is there, if its value is 1, if its value is 1, the machine must not fragment the data frame or the datagram. So datagram in the sense, whatever is the data is there or the packet is there, if its value D value is 1, then there will be no fragmentation. If it cannot pass the datagram through any available physical network, it discards the datagram and sends an ICMP error message to the source. It is saying like if its value is 1, means do not fragment. It is sending do not fragment. But its size is higher. So suppose in this case, it needs to send data from this token ring 4 Mbps protocol to this one. And here suppose the D value is 1. So D value is 1 means it is saying like do not fragment. But without fragment, the data cannot be sent to this protocol. That means it is saying no fragment and the data cannot be sent. So now here it has to drop that packet. So this packet will be dropped. If there is no fragmentation is allowed, but there is a requirement of fragmentation, so the packet will be dropped here. So the packet will be dropped basically. So here if the value is 0, 0 in the sense if the D value is 0, the datagram can be fragmented if necessary. So if it is D value is 0, then only the fragmentation can be done. So if this is the case, if here the fragmentation is required, in that case the D value should be 0. This is the basic idea. Yeah. The next is M. So M stands for more fragments. So more fragments in the sense, suppose packet is there, it is fragmented into different fragments. So suppose one fragment is sent, then next fragment, then next, likewise the fragments will be sent. So if a particular fragment is being sent, there is a value M. M is going to say like if the value of M is 1, it means the datagram is not the last fragment. So if suppose this is the first one, this is the second one, this is the third one, this is the fourth one. So if this is the first one, after this first one fragment, next 3 fragments are remaining. So in that case, the M value will be 1. Okay, so M value is 1 means the datagram is not the last one. There are more fragments after this one. So M value will be 1. Similarly, if M value is 0 means there is no fragment after this. So here also in F2 fragment 2, M value will be 1 because there are 2 more fragments available. Here also the M value will be 1 because one more fragment is there. At the last fragment, because after that there is no fragment left to send. So here M value will be 0. This is the value of M. How this flag basically indicates in terms of D and M bits, whether the fragment is required or not, or fragment can be done or not, or if there is a fragment done, is there any more fragments remaining or not? So this is D and M basically indicating. The next is like the fragmentation offset. So fragmentation offset is basically a 13-bit field. So it is a 13-bit field that shows the relative position of a particular fragment with respect to the whole datagram. So whatever is the position of the particular datagram or the particular fragment with respect to the whole datagram, that is indicated by the 13-bit field, that is called the fragment offset. The meaning is that how many number of data bytes are ahead of this data frame. In the sense, a data fragment in the sense, so suppose, so these are the different frames. So here the offset will be a value like before this, how many datagrams or how many fragments have already been sent, or what is the size of data that have already been sent. So offset, the value of offset here will be 0, because before F1 there is no fragment that have already been sent, or that there is no data that have already been sent. So this 0. Next, at this level, offset will not be 0 because before this there is already one fragment that have been sent. So suppose its size is 20. Suppose its size is 20 bytes or whatever is the size. Basically here that will be represented by offset, like this is the data that is already sent in the previous case. So that will be represented by the offset. So we will just taking an example here. Okay. So it is the offset of the data in original data frame measured in the unit of 8 bytes. So its meaning is like whatever is the original data byte divided by the 8 is the offset value. So in the sense, suppose a data uh, packet is there that is having of total 4000 bytes. So if a data is having 4000 bytes, means 4000 bytes, one data is there or one packet is there. So starting byte will be 000, the last byte will be 3999. So in that case, what will be the offset? So in this is the size. So in that case, what will be the offset? So offset will be calculated by the first byte. What is the value of first byte? That is 000 divided by 8. So always it will be divided by 8. So whatever is the offset will be for this packet, the offset will be the first byte divided by 8, that is 0. 0 is the offset for this. Suppose this is going to be fragmented. So we are going to fragment it into 3 different fragments. Okay. So in this 3 different fragments, so what we are going to do is we are fragmented such that the starting fragmenting with respect to like size 1400. So out of 4000, 1400 byte as the fragment 1. The next byte is again, next fragment is again the 1400 byte. The next fragment third will be like total 4000 fragments are there. So total 4000 is there. So out of 4000, 2800 bytes have already been gone. So 1200 bytes will be available into the fragment 3. So how it will be there? So once it is fragmented, so starting byte will be 000. The last one will be 13099. So because total is 1400 bytes. So 000 to 1399. So here in this case, what will the offset? So offset value for this will be the first byte position divided by 8, that is 0 will be offset. Next here in the fragment 2, the starting address will be 1400 after this 1399, 1400, and the maximum value will be like 1 less than 2800. So 2799 will be the last value of the second fragment because the size is 1400. So always the fragments will be divided into equal sizes. Okay, so 1400, 1400. So at the remaining one, whatever is the size with respect to that, what is the last one? That will be only 200, 1200. So it cannot be of 1400 because already the 1400 and 1400 is gone. The remaining is 1200 only. So here it is also divided into 1400. So the first byte is 1400 divided by 8. So it is coming out to be 175 is the offset for the fragment 2. Fragment 3 will be starting at 2800 and the maximum one is 3999. So offset will be 2800 divided by 8, which is 350 is the offset for the third fragment. One more point is like always it is divided such that the first byte should be divisible by 8. This is divisible by 8. It should be selected such that the first byte of each fragment should be divisible by 8. Okay. So this is the fragment part. So here the detailed example is given here. So here an original datagram is given for the same previous example. So bytes are 0002 to 399. So total is like 4000 byte is there. And the size of the header, the minimum size of the header is 20. So 20 plus 4000, that means 4020. This is the total length of the header as well as this is the header plus data. So header plus data is the total length. The total length is given by this 16 bit. So 4020 will be the total length. And this is the identification. This is the identification value. So identification value can be any value, any positive value, positive decimal value, or positive value that is of 16 bit. Okay. If this is the case, if it is fragmented, the identification value will be remaining same for the fragments. So this is divided into 3 different fragments. So identification value will be same for all the fragments. Okay. But here, what will be the difference? Yeah, one thing here, this is the M value. This indicates the M value. So M value is here 0. 0 in the sense, this is the first and last. There is no further fragments available. This is the first and last one. But once it is fragmented, so this is the fragment 1, this is the fragment 2, this is the fragment 3. So fragment 1 into the fragment 1 M value will be 1 because there are more fragments. So for fragment 2, M value will be 1. This indicates like there are more fragments available. So here in the last fragment, like fragment 3, the M value is 0. This indicates like there is no fragments available next to it. Means this is the last fragment. And what will be the offset? So offset will be the first one, it is 0, 0, 0. For the second one, it is 175. So that is calculated here, 175. So for the third fragment, the offset will be 350. That is calculated here, 350. Okay. And what is the value of bytes? Means this is the what is the total size? This is the total size 4020 with that is the total length. For the fragment 1, the total length will be 1400. That is the data plus header. So again, the header will be of 20 only, 20 byte only. So 1400 plus 20, that is 1420. So this is this 1420. Similarly, this will be the 1420. But for the last one, only 1200 bytes are available. So here only 1200 bytes are available. So 1200 plus 20 for the header. That means total size will be 1220. And the byte range will be, you can just look at it. Okay. So further, the fragment 2 is further divided into 2 different fragments. So fragment 2.1 and 2.2. So if it is further divided into 2 different types, so it's like 2 different parts. So it is like one is 800, size is one, means this 1400. So this 1400 is divided into 800 byte and the 600 byte. So 800 byte plus 20 will be the total length. So 800 data plus 20 is the header. So in that case, again, the identification value will be same as the original data type or datagram basically. Okay, and here also this is 1. This is 1. M value is 1 because there is more frames available or fragments available. So here is also M is equals to 1 because more fragments are available. That is, this one is the last one. So last fragment will be having the value M is equals to 0. Otherwise, they will be having the value 1. So yeah, so how this is 175, 75 is coming, the offset. So offset we need to calculate. So the range, once it is divided into 800 and 600, so 1400 plus 800 we will be adding it. So it will be coming out to be 2199. Okay, so for 800, so range will be here. So 1400 here. So the offset will be, for the first one will be 1400 divided by 8. So it will be coming out to be 175. In the second one, it is starting by 2200. So offset here will be 2200 divided by 8. That will be coming out to be 275. So this is the offset. So this is the basic idea, like how the fragmentation is done. Okay, so this is the role given, like if M bit is changing, if M bit value is 0, what is its meaning? So the value of M is going to indicate like what is whether there is next fragments available or not. If M is equals to 0, means there is no more fragments available, or we can call it like the particular fragment is the last one. But we can't say if the original packet was fragmented or not. A non-fragmented packet is considered the last fragment. So if it is a non-fragmented, also the M value will be 0. Even if it is fragmented, but the last fragment will be having the M value 0. So we can't tell whether it is fragmented or not, but we can say like it is the last fragment basically. So similarly, what is the value of M is equals to 1? Then what is its meaning? Similarly, the value of M is 1, and also the fragment offset value is 1. So what is the meaning is given? You can just go through it. The same is given with an example like if the offset value is 100, then what is the number of first bytes? What is the number of first byte? So if this is the offset is given, so number of first byte will be 8 multiplied by the 100. That is 800 is the byte, the first byte of the fragment basically. Byte number is 800. So likewise, the different combinations are given. You can just go through it. Okay. One more thing, the checksum. So here in the checksum part, the same checksum we have already seen. So here how the checksum is basically calculated. That is basically for error control or error detection into the header. So header is having different values of the bytes. So this is the first, second, third, fourth. Okay. So different components are there. So this 4 and 5, 4, 5 and 0. These are considered to be like byte 1, or 4, 5 and 0, that will be considered as the 16 bit. So this is 16 bit and this is the 16 bit. So it is basically going to add it. Okay, so 450, 45 and 00. This is 8 bit, so 00. 28 in hexadecimal will be represented by 001C. 1 will be represented by 0001. Then 00 will be 00. 4 and 17 will be 4 and 17 will be represented likewise into hexadecimal. So 4 will be the same and 17 will be represented by 1 1. Similarly, this 10 and 12 combinedly will be 10 and 12 will be of 16 bit. This because this is of 32 bit, 16 and 16, 32 bit IP address. So all these data will be added to get a sum. Then its complement is there. Complement, that will be the checksum. So this is the checksum. This checksum value is stored into the checksum value of 16 bit. That will be basically used to identify any error that is available into the header. This is the basic idea of the checksum. So checksum we have already seen in the previous module. Okay, so one more point is there, that is options. So what is the options? So options, as the name implies, are not required for the diagram. They can be used for network testing and debugging. So they are basically used for network testing and debugging. So they are having different types of options, single byte and multiple bytes. So what is its meaning? It is given here. You can just go through it. Okay. So that was just a theoretical part only. Yeah. So like record route in the sense like if a sender is there and a receiver is there, in between there are some routers. Okay. So once it is sending the data, it will be recording. So record route means sense it will be recording the route. This is router 1, router 2. So this is destination sender. Along with that, it will be recording the route like it is passing through R1. Once it is going here, it will be recording like destination source and then R2 and then R1. So likewise, it will be recording the route. That is the basic record route. Strict source, load source means strict source route means if it is fixed, the route is fixed, it will be strict route, strict source route. Loose source route in the sense some routes are fixed and some are not. So some routers are fixed, means the data should be passed through some routers that are the loose routes. Okay, loose source routes. So they are a basic idea. You can just go through it.